Imagine trying to build a deep space exploration vessel by just grabbing a winch and hoping for the best. For something that complex, you need blueprints before you ever tighten a single bolt. Building a massive software system follows a similar logic. Before anyone types a line of code, developers go through software project planning. This is the phase where a team figures out exactly what needs to be built, how long it will take, and how to manage the work. This sequence starts with the requirements. From there, we estimate the size of the project to set a budget and build a realistic timeline. All of those estimates funnel down into two final steps: resource allocation and risk management for potential problems. When this sequence is ignored, projects often run out of funding while the core logic is still unfinished, or teams realize too late that the different parts they've built don't actually fit together. So, how do you measure the size of a digital project that hasn't been built yet? One method is lines of code, or LOC. You simply estimate the total number of lines the programmers will write. It's easy to calculate, but it doesn't account for the difficulty of those lines. Writing 10 lines of complex logic can take much longer than writing 100 lines of simple text. An alternative is function point. Instead of raw text, it measures what the user sees and does. The system is broken down into 5 pieces, counting external inputs like a login, outputs like a report, inquiries, and internal data files. If lines of code measures the physical volume of the work, function points measure the actual capabilities of the system. By focusing on features rather than raw text, developers can predict the work required much earlier in the process. Once the team knows the size of the project, they use math models to calculate the cost and the amount of human effort needed to build it. This formula is part of a model called CALCOMO. It uses the total amount of code, measured in thousands of lines, or KLOC, to predict the work required. Think of KLOC like the square footage of a house. A larger number takes more effort. CALCOMO categorizes projects into 3 complexity types: organic for small, semi-detached for medium, and embedded for highly complex systems. But knowing the cost is only half the battle. Managers also need to know how many people should be working on the project at any given time. This is the Putnam Resource Allocation Model. We visualize the staffing flow using the Rayleigh curve. The number of developers starts low, peaks, and gradually drops off. This wave means a few architects at the start, a massive construction team in the middle, and a small testing group at the end. Using these cost and staffing models together ensures the project has the right number of people and the right budget to reach the finish line. Even with a perfect budget, unexpected problems can derail a project. Effective planning includes identifying technical hurdles or market changes before they happen. When a risk is identified, teams use 4 strategies. They can avoid the risk, reduce its impact, transfer it to someone else, or accept it with a backup. With the risks managed, the focus shifts to the internal architecture. This is the software design phase, where requirements are turned into a structural map. To build a sturdy system, we want functional cohesion, where parts inside a single module work together to do exactly one job perfectly. We also want message coupling, where independent modules talk through simple, clean connections, rather than being tangled up and breaking the system. When internal parts are focused and external connections are simple, the system is easier to maintain. If one part fails, the rest of the software can smoothly keep running without causing a total system crash. This independence is the core of object-oriented design. Instead of seeing software as a long list of commands, it treats the system as a collection of self-contained digital objects, each holding its own data and instructions. This design is built on 4 pillars, known as EIPA. First, encapsulation, which is like a protective shell hiding complex data. Then, inheritance, which lets you reuse code from old objects in new ones. Next is polymorphism, the ability for one command to work in many different ways. And finally, abstraction, which is like a simplified dashboard that hides the messy engine underneath. While those pillars keep the engine running, the user interface is the cockpit where the human operator actually interacts with that complexity. A good